let's continue on. I guess I wasn't watching the clock too closely on that last one. Now, the key thing to remember is that what this means is you're talking about the concentration of the copper ion. What this means in brackets like this is it's the concentration of the bromide ion. Okay, so it's the concentration of this times the concentration of this equals this particular number, which is the solubility product equilibrium constant. Okay, so the concentration of this times the concentration of this equals this particular molarity. Okay, and so that's so that the concentration of each one of these can be determined if you know this particular value and it's written correctly. And so this times this is x squared equals that 68 times 10 to the minus 10th. And the reason why they have this as 10 to the minus 10th here is because that makes it a lot easier when doing a square root, is because then you can just take this value and cut it in half, right? So 1/2 of 10 is 5. And the square root, so you then have the square root of this number times 10 to the minus 5th, and that gives you this number right here. Okay, that's it's really fairly simple once you work through those. Just to show you how that works for something else, here you have calcium hydroxide, and when this solid is dissolved, it forms one calcium ion, but you notice it forms 2 of the hydroxides for each one of these that it forms. So for every one here, you're going to get 2 of those here, aren't you? So that means at equilibrium, you're going to have X concentration of this one right here. You're going to have 2x times this one. Okay, and this 2x is raised to this second power, second coefficient here. So not only do you have 2x, you have 2x squared, so it would be 4x squared here. So this right here would be 4x cubed equals this right here. You leave this as 10 to the minus 3rd. 10 to the minus 6th, because that is easily divided by 3, isn't it? 6 divided by 3 gives you a minus 2. And the cube root of 1.3 is 6.8. Okay? So that's how you determine the individual concentration. So the concentration of the calcium ion is going to be 6.8 times 10 to the minus 2. The concentration of the hydroxide ion is going to be twice that, isn't it? It's going to be 13.6 times 10 to the minus 2, right? 2 times 6.8 is 13.6. Okay? So you see how, depending upon what you have to make certain you have the equation correct up here first, and the coefficients that are in front here not only affect the number of particles here, but they also raise this solubility coefficient to a different power. Okay? Those are key things you have to remember about using these equations. So, these values can be used to predict whether a precipitate will form when ions are added to a solution. Q is called the reaction coefficient, the reaction quotient, okay? That involves all of the different ones involved here. Q is the same form as this. The only difference is the concentrations at any particular moment can be used with Q, and only equilibrium constants are used with this one right here. KSP only is correct, that value is only correct if it's at equilibrium. If it's not at equilibrium, in other words, you could put more in there, this value is what you would be using. It's the reaction quotient. For any reaction whatsoever, what you have is the concentration of the products divided by the concentration of the reactants. Okay? It also has the rule that for this particular one, that would be a 1 in the denominator. Sometimes you will have more than one material over here, so that it becomes, you actually do have something in the denominator here. but it will not be the case for a solubility product, because for a solubility product, you're always going from a solid into something that's dissolved in the material. Okay? This is the Q is the more general term. The KSP only exists at particular points where you actually have equilibrium established between the ions in solution and the solid that's not dissolved in the solution. So the relative magnitude of Q versus it will indicate whether or not the precipitate will form. So if you have a solution and the Q is much greater than KSP, a precipitate will form, decreasing the ion concentrations until equilibrium is established. If this is less than QSP, the solution is unsaturated. No precipitate will form, and if desired, more compound can be dissolved. Okay? So it's unsaturated, no precipitate will form at that particular time, and more can be dissolved. In a solution is saturated, Q equals KSP, and this is just at the point of precipitation. So when it is equal to that, that means you have as many ions being formed here as you have ions going back this way. That's the reason why you have the forward arrow and the backward arrow. Forward arrow and backward arrow means you're at an equilibrium. This does not mean that nothing's happening. Quite a bit is happening. This is still dissolving into this, but the amount that is dissolving into this is equal to the amount of these that are forming back into solid materials. Okay? That's a saturated solution is when that occurs. Okay? And so it's important to understand the relationship between what Q is versus the KSP in terms of whether a precipitate will form or whether if you add something to the material, more can be dissolved in it. Here you have barium sulfate solid going into barium ions and sulfate ions. Now, what happens if you add sodium sulfate to that solution? Okay, this is called the common ion effect. Because you have a common ion, the sulfate ion here and the sulfate ion here, that means that you're going to have, instead of just having 1-to-1, as you would expect from that prior equation, x, where this would be x and this would be x, this is x plus a bit more, isn't it? X plus this 0.1 molar. So by Le Chatelier's principle, this common ion, having more of these, is going to drive this back in this other direction. So that common ions reduce solubility. There's other properties that are very interesting for water as well. If you put these ions in solution, they're going to conduct electricity, aren't they? Because you have ions that can migrate from one pole to another pole. And that essentially completes the circuit from the battery through the light bulb, and so the light bulb will show up. If you have instead alcohol or sugar or other non-conductors in there, they're not going to conduct electricity. Your bulb's not going to light up. So the idea is ionizations, molecules that can form ions, can dissolve in material and form ions. You will get, those are called electrolytes once they're in there because they're carrying a current, right? That's from the Greek. This portion means that it can carry. This right here means it's a charge, right? So it's carrying a charge from one side to the other in this particular instance. Now, when things ionize like that, molecules are formed, ions are formed from the molecules, and this occurs as polar molecules dissolve in water. Okay, water itself does not conduct electricity unless it has impurities in it. If you put acid in water, you will get a hydronium ion and a chloride ion. Okay, this is an acid right here, an acid. Okay, and And you can look at that in a couple of different ways. You can look at it the Lewis acid approach, or this right here is just the charge approach. Now, putting something into water affects its boiling point. The normal boiling point is the temperature where the vapor pressure is so that there you all of a sudden the molecules as a liquid start going into molecules as vapor. The vapor pressure over a solution is less than that of a pure solvent. Okay, solute particles displace some of those. Okay, you can visualize it here. So instead of having just all of these available to go into the atmosphere, now you've got some different things taking up space here. And what that leads to is higher boiling points, because these hinder the movement of things going from here to here. Okay? That's called boiling point elevation. It's what we call a colligative property. Okay? Colligative property. C-O-L-L-I-G-A-T-I-V-E. It's called boiling point elevation. That's just one colligative property. So, for example, and that doesn't matter. If you have covalence, whether it's a covalent solute or an ionic solvent, the thing is that if you have dissolved sugar in here, that's going to raise the boiling point to a certain degree. However, if you have the same amount in terms of moles of sodium chloride dissolved in there, you can see each sodium chloride molecule is going to have one ion of sodium, one ion of chloride, right? So it's much more than just one molecule of this. So 1 mole of this, it gives you 1 mole dissolved. 1 mole of this gives you 2 moles of ions in there. And with calcium chloride, you'd have 2 chloride ions, 1 calcium ion. So you'd have 3 times as many, okay? So equal molar solvents lead to approximately the same boiling point increase. The ionic solutes provide more solute when dissolved in the aqueous solution. It depends upon how many ions can a given material form. 2 in this case, 3 in this case. So it means quite a bit of difference in terms of the ability for these salts to raise the boiling point. Not only that, but it also causes freezing point depression. And the kinetic energy of molecules reduced enough to allow crystallization. The presence of those solute particles interfere with that crystal formation, leading to freezing point depression. And that's why you use calcium chloride as opposed to sodium chloride when you want to dissolve the ice on your sidewalks. That's because you're going to have 3 times the ions, 1.5 times the ions that you would have with just sodium chloride itself. So ice is practically pure water. The salinity of seawater increases, okay, when you have ice over it. Antifreeze, ethylene glycol, adding those are the things that you add to your battery. So your battery will still be able to turn over your motor during the winter time, right? So that's the key point about that freezing point depression. Now, let's go on to acids and bases in aqueous solutions. First of all, the definition of an acid. Johannes Bronsted and Thomas Lowry in 1923 came upon this type of definition. What they wanted to do is they wanted to focus on the proton or the hydrogen ion. Okay, for a Bronsted-Lowry acid, it's a compound that donates a proton to another compound, and a Bronsted-Lowry base is one that accepts a proton from another compound. Okay. For Arrhenius definitions, the Arrhenius acid definition is one that donates a proton, yes, but an Arrhenius base is one that has excess amount of hydroxide ions. So it looks at it as Arrhenius is in terms of protons or hydronium ions and hydroxide ions. This is in terms of protons being donated or protons being accepted. And that's it for this section.